All right, so Friday is exam 1. And the topics are problems up through strain number 6. So the things that you need to know how to do are you need to know the meanings of the strains. You need to know how to use the compliance matrix. And there was one more. Tensor test. You need to know how to do it, like take the measurements of a tensor test and then use those values for a compliance matrix. Anybody have any homework questions that are relevant to the test? So I say up through strain number 6, but there are other questions later on that where you have to do those same things. So if you want more practice, there are other problems you could look at later than number 6. But there won't be any topics that are introduced after number 6. Okay, so yeah, homework questions? Yeah. Yeah, we skipped those last two. That's right. So the last two are just sort of more geometry questions than it's a lot of work for not much payoff, I think. So I'm just skipping it. Yes. 12B. Anybody have the questions with? I think by now I would anticipate that I would get the question. Okay, so first you need the values from the tensor test in number 10. Does anyone happen to have those numbers? So 12 uses the values that you get in that tensor test. Stress. Oh, what number? What on strain? Oh, is this strain? Oh, I got you. Okay, so those two are each 15. This is all in megapascals. Then we got this one and this one. And those are each 2. And then we have this one, 25. And so the stress tensor, so the coordinate system is like x this way, y this way, z out. So the xx stress is positive 25. There's no xy. There's a negative xz of 2. So negative 2. And then 0 because of symmetry. There's no yy. There is a yz of positive 15. And then symmetry, symmetry, and no zz. And this is all megapascals. So that's the stress tensor. And then for part B, this is a good introduction to the next topic. We have this thing like this. You could imagine this being like a finite amount of material. And this angle is 30 degrees. And this is in the XY plane, this picture. And so we want to know on this face, what's the traction? So what's the traction vector on the shaded face? Well, what we need to do is come up with an outward-facing unit normal. So if you draw the coordinate system, draw that a little straighter. Okay, so there's the coordinate system. And first I'm going to, so all the vectors that I'm going to draw are going to have their tails at the origin. And first I'm going to draw the one with a given angle. So first I'm going to draw one this direction. Okay, that's an angle, that's a vector that's parallel to the face. And that means it makes a 30-degree angle with horizontal. Okay, so if you're going to use cosine and sine here, your angle theta for this one is just positive 30. And now an outward-facing normal is 90 degrees from this. And actually, there are two vectors that are 90 degrees from this. There's one going this direction and one going this direction. So we want the one that faces out of that surface, the alien for that, you know. Have you guys, did I assign that watching Aliens yet, just to make sure you understand an outward-facing unit normal? You have to watch the whole movie just to see the alien burst out of someone's stomach. But the outward-facing, so this would be an inward-facing unit normal. We want the outward-facing, so we want something 90 degrees that way. So now I'm going to draw that. Okay, these two are right angles from each other. And so that means that this vector, the one that we wanted all along, theta is equal to plus 30 plus 90, so 120 degrees. And so that means that the outward-facing unit normal in hat is equal to cosine of 120, sine of 120, 0. And that is negative 0.5, positive 0.866, 0. And now to get the traction on that face, you just multiply the stress tensor to this. So the traction vector is what we got before, 25, 0, negative 2. Symmetry, 0, 15, 0, nope, negative 2 from symmetry, 15, 0. So that's the stress tensor, and then we're going to multiply it by the outward-facing unit normal. And that gives negative 12.5, 0. Oh, we almost got through without, so 1, I can't do that. 13.99. And this is all in megapascals. So that is, those are the components of the traction vector on that face. Okay. Sure. Any other homework questions? In that problem? In that problem, it asked for it on this shaded face. Okay, so if it asked for it on the positive z face, you would multiply this times 0, 0, plus 1. Negative face, 0, 0, negative 1. But in a more complicated problem, it's not just one of the faces that you already have in the cube. It's asking what it would be on a face oriented with one of these funny directions. Why would you want to do that? We'll really see the most important answer for that in the next topic that we cover. Okay. Well, the z is out here, so that would just be the side of this triangle, and that would just be the same as the. So the only one there's only one face here, one surface that's at a funny angle with the coordinate system, and that's the one we used.
Had you asked to rotate above the y-axis, what would change about them?
Rotated about the y-axis.
Would it just be instead of 0 for 0?
Okay, so what if I had said, okay, this is fake part C. So what if I gave you something like this instead? You have a surface like this, and this is 20 degrees, and let's say that our coordinate system, this is our x-axis, and this is our z-axis. Okay, and we want to find the traction vector on this face. How do we do that? First of all, what direction is the y-axis facing? The positive y. What? It is towards us. Yep, that's right. So if you go x cross z, you think that has to be y, but y always has to be the weird one. So then you flip it. And so the positive y is coming out. And so this face is rotated. You can think of it as rotated tipped up that way from the old z-axis. Okay, so how would we represent this? So I think when you were asking about like a rotation about the y-axis, you might have been sort of thinking of the rotation matrices. That's not what we're doing here. Although, I mean, you could come up with a rotation matrix that would re-express your old stress tensor in a coordinate system where that's an axis, but that's not this.
So the normal vector value is different.
Yeah, so to get that normal, that outward facing unit normal. So first of all, why do I always show it as a wedge? Did I clear that up last time? Like, why didn't I just show the line? There's an important reason. It has to do with the Alien movie. Because you have to know whether the alien, the alien has to go out of something. So you have to know where the material is, Is this the material and this is the edge? Or is this the material and that's the edge? Okay. And so the outward facing unit normal that we want goes that way. And so to get that, so here's the z-axis, here's the x-axis. So this is one where using a rotation matrix might not be a terrible idea, but let's not do that. So what are the, so first we'll use the angle that's given. So I'll put a vector over here. That's supposed to be that 20 degrees. And going counterclockwise. Okay, so now we're doing a rotation about y, so that's why you have to know the direction of the positive y-axis. But we're going, in the positive y direction, right-hand rule from x down to there. So that's 70 degrees. Okay. And from there, we want to go 90 degrees. So we'll go plus 70 minus 90, so negative 20. And then that unit, well, so we just have to come up with the components of this unit vector. I guess it's a little different in this case because, so you can't just think of this as cosine and sine. That only works for the x and y axes. But if you think of this as a right triangle, that angle is 20. You can get an x component of cosine of 20 and a z component of sine of 20. So this will be, so this outward facing unit normal is 0.940, negative 0.342. That's just doing the trigonometry of that triangle. And that should be the z. It would have been better if you wouldn't have asked this, to be honest. Yeah. Okay, now I'm realizing right now that I'm going to keep it in the XY. But anyways, you'd have that, and then and now it's the same, just take that stress tensor, multiply it by that outward facing unit normal. So the traction on that face is just the stress tensor times that. Okay. Any other questions about this? Yeah. Okay, 2. That's crazy. Straight. Okay. All right, so this question is a little confusing unless you, probably the easiest way to make sense out of it is to just look at the wording and then try to guess what kind of thing in this area might I be trying to get at. I think the wording is sort of confusing, but strain number 2. So based on the matrix relationship between stress and strain given in class, so first it's asking for the dependence, like what stress values the different normal strains depend on. Okay, so C asks, well, here's the relationship. The relationship is the Voigt strain is equal to the compliance matrix okay, half done. Times the Voigt stress. That should be YY. ZZ. And then you can keep writing sigmas, or this time I'm going to write it as taus. It means the same thing. And now just do the matrix multiplication to come out with the relationships. So the XX strain is equal to 1 over E times sigma XX minus nu over E times sigma YY minus nu over E times sigma ZZ. And so the XX normal strain by itself depends on 3 normal stresses. Okay, and that's true for every one of these normal stresses. So finally, I'm at part D. It asks for the equation relating the YY normal strain to the other stresses. And so we have EYY is equal to negative nu over E sigma XX plus 1 over E sigma YY minus nu over E sigma ZZ. And you get a similar thing for the Z. And then once you get down to the shear strains, the relationship is the YZ shear strain is equal to 2 times the quantity 1 plus nu over E times the YZ shear stress. And then that relationship sort of holds for the next two. Okay, so if you want to calculate, say the only thing you want to calculate is the XX normal strain, then in order to get an accurate value for that, you need to know all 3 normal stresses. Okay, if you're doing it calculating from the stresses. I mean, you also could just do it geometrically if you've taken measurements of how it deforms. But most of the time, we're going to calculate the stresses and then use the compliance matrix to come up with the strains. Okay, so you don't have to do it as a matrix equation. You can do it one by one like this if you just want individual values. But if you have the matrix programmed into your calculator, it doesn't really save you any time. This is maybe I think it's a useful way to think about it. Maybe it lets you see what kind of things matter. Like if you wanted to calculate EXX and you weren't sure, but you didn't know what the shear stresses were. Okay, you knew what the normal stresses were, but you didn't know what the shear stresses were. This tells you that you could get that answer accurately. Okay, but if you didn't know what sigma YY was, you couldn't get an accurate answer for EXX. Okay, so that's what this is about, just understanding what strains are tied to what stresses. And by the way, it works, the inverse of this works too. The coefficients are different, but if you're trying to use the stiffness matrix to calculate the X normal stress, you'd need to know all three normal strains, okay? Same with calculating y, z, z. But then when you get to the shear, if you're trying to calculate a shear stress, all you need to know is that corresponding shear strain, okay? This is called the Poisson's effect, the fact that a normal element depends on all three normal elements, because if you squeeze the sizes, it bulges out the top and, you know, all the different versions of that. But there's nothing like that with shear stresses and strains. There's no Poisson's effect with shears.
The shear stress, that's just the stress along the face.
Yes, that's right. Along the face, yeah, in the direction of that axis. Any other questions about that one? Any other homework questions? Okay, so the next topic is principal stresses. Here's a surprising and amazing fact. For any stress tensor, there's a coordinate system where that stress shows up as only normal stresses. Okay, so you can make up any stress tensor, just make up numbers as long as it's symmetric. Somewhere there's a coordinate system where if you use the rotation matrix to transform that stress tensor into this new view, you know, if you think of the coordinate system as just a way of viewing or a way of measuring it, where that same state of stress shows up as only XX, YY, and ZZ elements, no shears, okay? For like a material, that means, you know, load some body. Okay, so if I press down on this, I'm creating stresses over here by the hinges, and we could measure those stresses and we get some shears and some normals. And then we could convert it to a coordinate system where if we had taken those measurements in that coordinate system to start with, all we would have is normal stresses. It's a little surprising because you kind of have this feeling that shear stresses and normal stresses are fundamentally different things. You know, a shear stress, I mean, the name of shear stress is because you sort of create those stresses by doing what scissors do to a material. You push down on one side and push up on the other side. But it turns out that the fact that it's a shear stress really is just has to do with what your coordinate system is. Okay. Okay, well, that is, you have to give me that. It's pretty surprising. But whether it's useful is not clear yet. But there's another surprising and amazing fact. in that principal coordinate system, one normal stress is the maximum you can find anywhere, the maximum you can find with any coordinate system. And another one is the minimum you can find with any coordinate system. Another normal stress is the minimum that you can find with any coordinate system. Okay, well, that makes it sound a lot more believable that this is something useful. Because for any state of stress, like you're doing something to a big lump of metal or something, your coordinate system tends to be just based on like what's easy for you to measure, So how do you compare a stress tensor in this random coordinate system to another stress tensor over there? Is there any way to quantitatively measure which one is a bigger stress or more likely to damage this material? Well, if you can find this coordinate system where everything is represented by these principal stress tensors, then you can say, okay, this maximum is bigger than this maximum, and this minimum is smaller than this minimum. It gives you a way to compare these matrices of values, okay? So are you with me on that? That seems like a useful tool for, and then there's one more, this is the last one. Another surprising, amazing fact. Once you find those principal stresses, it's easy to calculate the maximum shear stresses that you could find with any coordinate system. And so once you know the maximum and minimum normal stresses, and the maximum shear stress, you can determine the likelihood of, failure, of this thing reaching whatever failure criterion you're concerned about. Okay, so that's why we want to calculate these principal stresses. So you're given this any old state of loading. You're given all the stress elements in some random coordinate system, and you want to find the coordinate system where that loading can be represented with only normal stresses. So first of all, that gives you the maximum normal stress that you could find if you rotated that coordinate system all around. You'd look at all the normal stresses at all the coordinate systems. This principal one has the maximum and the minimum. And when I say minimum, I don't mean minimum absolute value. I mean maximum compression if it's in compression. So you can think of this as like maximum tension and maximum compression. And then with an easy calculation from there, you can calculate the maximum shear stress value that you could have with any choice of coordinate system. And using those values, you can say with some confidence whether you're concerned about this steel thing that's built into the door or whatever being damaged by the loads. Okay, that's the idea here. Okay, so how are we going to find the principal stresses? And calculating the principal stresses is an eigenvalue eigenvector problem. And the basic idea of an eigenvalue eigenvector problem is you have some matrix and you multiply it by some unit vector. Multiplying it by that matrix gives you a vector that is parallel to that original unit vector, and the magnitude is changed by some factor lambda. Okay, so that's the definition of an eigenvalue eigenvector problem. And these are going to come up in all your classes basically starting now. Okay. So what's special about this equation? And I haven't talked yet about how this relates to what we want to do, but it comes up in a surprising number of calculations that are important in engineering. What's different about this problem than any other matrix calculation? Like in general, if you multiply a 3x3 matrix times a 3-element vector, okay, you're always going to get a vector back. But in general, that vector is going to be not just have its magnitude changed, but it's going to be rotated in some way. Okay, like try it with, like, doesn't that always work? No. For example, let's take this matrix 1, 3, 6, 0, 2. Let's even make it symmetric because we're going to be dealing with a symmetric matrix 6, 1, 0. Okay, and multiply it by the vector 0, 1, 0, just to make it easy to visualize. The matrix you get out is 3, 2, 1, which is clearly not in the same direction as 0, 1, 0. Okay, but in this eigenvalue equation, this is the same direction as n. Okay, So that's what we're looking for. We're looking for special cases where multiplying the matrix by a unit vector gives you a new vector that's in the same direction. All right, so I guess before I go into the calculation, let me derive how this comes about in our problem. Okay, so this is the derivation of the Eigen problem for principal stress. So let's start with this stress tensor. I'm going to call it sigma xx, xy, xz. I'm going to take advantage of the symmetry. And now we're going to use the idea that if you multiply the stress tensor by a unit normal vector, a unit vector, it gives you the tractions on the face that it's normal to, right? So if we're looking for a face that only has normal stresses, and we multiply this by, this outward facing unit normal, what would it mean for that face to only have normal stresses on it, only have normal traction component on it? Can you picture that? So basically, you can think of this unit vector as the outward facing normal for whatever unit vector you give. That's the outward facing normal vector to some face, okay? And if that face only has normal traction components on it, what's the relationship between the outward facing normal and the traction vector? Same direction. So yeah, how am I going to illustrate this? So if this is your face, this is your outward facing normal. Well, if that face only if that doesn't have any shear components to the traction vector, then it's going to be just parallel to that vector. It could be in or it could be out, depending on what the factor is that you're multiplying it by. But it's going to be in that same direction. So the normal goes that way. The traction can go either way. I'll draw it the other way just so you. Okay. And so we can write this as lambda times this same unit normal. And so the idea is that we're trying to find a face where the outward unit normal and the traction vector are in the same direction. So now how do we solve that? How do we come up with So what we're trying to do is we want to find, we need to find two things. We need to find the outward unit normal. That's n hat. And that's what's going to be called the eigenvector. And we need to calculate the lambda, that constant of proportionality, and that's called the eigenvalue. And that's the principal stress value. That's a good question. It doesn't have to be, but multiplying it by a number doesn't change anything. So in order to give a unique answer, you want to treat it like it's going to be a normal, because it works for n and it works for any number times n. Okay, so might as well just give the normal. All right. So this equation, we have it up here. Okay. And I'm going to rewrite that as, so write out these elements again. And multiply it by the outward unit normal again, nx, ny, and z. But now I'm going to rewrite the right side. So notice that I can rewrite this as a lambda times a matrix with ones on the main diagonal and zeros everywhere else, times that same unit vector. Okay, this is called the identity matrix. Why would you call that the identity matrix? Like what happens to any vector you multiply to this matrix? It gives you back the same vector. So putting this in here gives us exactly the same value as if it wasn't here at all. Okay. But now that I've done that, well, let me rewrite this again one time. So now I'm going to carry that lambda through this identity matrix, and we have just lambdas on the main diagonal. Okay. And now I can subtract this from both sides. Because each of these two matrices is multiplied by the same vector. Okay, so now I'm going to rewrite this like this. Sigma xx minus lambda, sigma xy, sigma xz, sigma xy, sigma yy minus lambda, sigma yz, sigma xz, sigma yz, and then sigma vz minus lambda times that unit vector is equal to 0. Okay. There's two types of solutions to this. The first one is the trivial solution. And that is just so let's see. That is that nx equals ny equals nz equals 0. Okay, that one's useless to us, so we don't care about that one. We want to make sure that we're not getting that one. The one we want comes when this matrix is not invertible. So we're going to require that left matrix is not invertible. And we're going to do that by finding where the determinant of that matrix is 0. So set the determinant equal to 0. And that's where we'll stop right now. So we have this equation with this matrix, just a matrix of numbers, and it's still symmetric because all we've changed are the diagonal elements. And we're going to set the determinant equal to 0. That's going to give us 3 different answers for lambda and 3 different corresponding answers for that unit vector. And those are going to be the coordinate system directions for our principal coordinate system. Right. I know that was all pretty abstract, but I'll talk about how to do the calculation. I'll talk about how to where to go online to just have a computer do the calculation for you. And then we'll do some, examples. Okay, test Friday.